esto son los resultados, con más de 500 publicaciones. Y no es necesariamente el número de publicaciones lo que recalco, es la calidad de sus publicaciones, como lo refleja el número de citas bibliográficas, 47.950, y un H-index de 110, considerado como uno de los científicos más citados en el mundo en ciencias de los materiales y química. Y esto está listado en mentes científicas más influyentes del mundo. Ha dado más de 100 conferencias plenarias y magistrales. Tiene 24 patentes y es doctor honoris causa de varias universidades. El profesor Lu, desde su comienzo de la carrera académica, ha considerado vital tener en cuenta el impacto social de la investigación, cuáles son las necesidades sociales y qué es lo que se puede hacer para lograr una diferencia en el plano social. Y concuerdo ampliamente en esto, porque incluso hemos incluido ONG en proyectos de investigación para dar oportunidades a los sectores menos privilegiados de la población, donde hay un enorme potencial humano escondido por falta de oportunidades. Además, el profesor Lu considera prioritario la colaboración universidad-industria. La Universidad de Surrey es una institución pionera en esta área, ya que fue una de las primeras que introdujo el año industrial en el pregrado. En cuanto a sus actividades relacionadas con Argentina, el profesor Lu ha trabajado por muchos años con el científico argentino profesor Jorge Beltramini, a quien lo incorporó en el Centro de Excelencia para Nanomateriales Funcionales en Queensland, Australia. Ellos tienen muchas publicaciones en conjunto. A través del profesor Beltramini y el profesor da Costa, el profesor Lu tuvo mucha interacción y colaboración con los profesores Carlos Apesteguía e Isabel Di Cosimo de la Universidad Nacional del Litoral y CONICET. Durante su periodo como vicerrector para investigación y provost de la Universidad de Queensland, Australia, el profesor Lu promocionó fuertemente la colaboración bilateral entre Argentina y Australia y organizó la visita de su excelencia, el embajador argentino Pedro Villagra, a quien se le otorgó un doctorado honorario de la Universidad de Queensland. Desde 2016, como presidente y rector de la Universidad de Surrey, el profesor Lu ha apoyado activamente la colaboración entre académicos de Surrey y Argentina. Hemos realizado numerosos viajes y también con motivo de la firma de un convenio de colaboración con el Instituto Nacional de Tecnología Industrial. Estas visitas fueron impulsadas y financiadas por el profesor Lu. También se han publicado trabajos científicos con la participación de ambas instituciones. Lógicamente, la brillante y excepcional carrera académica de Max Lu motivó mi interés en su incorporación como miembro de la Academia Nacional de Ciencias Exactas, Físicas y Naturales de mi país. Y agradezco a los miembros de la Academia el enorme apoyo que han dado para que esto se concrete. Y realmente es un día muy especial para la Academia y también para mí. Muchas gracias. Bueno, un segundo. Luego de la entrega del diploma, luego de la entrega del diploma, el título de su conferencia es Green Hydrogen Production and Storage, Materials Innovation. Producción y almacenamiento de hidrógeno verde, innovación de materiales. Muchas gracias. Dentro de un momento lo vamos a tener.
is to receive our most grateful warmest welcome to our academy. And on behalf of the academy, here is the diploma that accredited as a new member of the academy. And this is also very important, is the pin for our academy. Thank you. Thank you so much, President Ramos. You're going to take a seat. Okay. Shall we start now? Yeah. Well,
Turn on the audio.
presentation, right?
Yes.
Okay. Podemos girar ella para que se ilumine.
Sí.
Okay. President Victor Ramos, distinguished fellows of the Academy, ladies and gentlemen, it's a great pleasure for me to be here with my colleagues, my wife, and Patrick and Tom from the University of Surrey, of course, Angela. I would like to thank President Ramos and the Academy for such a great honor. I'd like to thank Angela for very kind, long introduction that I don't recognize. A lot of things that you described there, maybe I should learn more Spanish, but I'm really, really grateful to the very kind introduction. So I'm truly humbled and honored to be inducted into this august academy that has so many distinguished fellows like you all in the audience. And I do recognize a few friends here, Naomi and Uncle Garo. Today we met at USAM. I know that the Republic of Argentina is at the forefront of science and technology. For example, I know you have a very fine tradition in the sciences. And of course, this academy has been a leader in advancing the sciences. And of course, you have 5 Nobel Prize winners, including 2 in medicine, 1 in chemistry. I know very well Professor Louis Lenoir, and of course Professor Cesar Melsen's medical work. I think as a Chinese Australian, when I was in Australia, I already learned Argentina is also at the forefront of medical research, because you should be proud of the fact that you have Professor Dr. Renee Travaglaro, who actually was the first coronary bypass operations, and Julian Palmes is the balloon stent that have saved millions of lives around the world. So without further ado, I'd like to give my lecture on hydrogen and green hydrogen production and storage, mainly from a materials innovation perspective. I'd like to start by just showing a few slides about the University of Surrey, because I'm the head of the organization. I'm very proud of the achievements of the university so far, and my colleagues also joined me on this trip, especially to visit Buenos Aires, and also we're going to fly to Brazil tomorrow. The University of Surrey is one of the top universities in the United Kingdom. It has 16,000 students and many international students, non-UK students. So overall, we contribute 1.9 billion pounds to the UK economy, and we have around 78 million worth of research innovation income as research grants and from foundations and from councils and other research contracts from industry. And more importantly, I think we have the second biggest research park that we own that's on our campus that has 174 companies. And that form a good ecosystem for innovation. I won't bore you with a lot of numbers. I think we ranked fairly highly in the United Kingdom. In the world, we are around 230 overall by the Times Higher Education ranking. And we're very proud of the fact that the university's mission and the university's activities, both in education and research, contribute to UN SDGs. Therefore, we rank 55th in the world in terms of the impact ranking by Times Higher Education. We have disciplines that is, such as tourism and information technology, food science, paramedics, and nursing, all in the number 1 or number 2 position in the United Kingdom. We really claim, we can claim the dual excellence in both teaching and research, but also high impact in regards to contribution to society. We have won a lot of awards, Queensland University Prize 4 times, and then the Royal Academy of Engineering Prize, for the first time the Foundation Prize, inaugural prize won by our 5G Innovation Center. And we have Gold Teaching Excellence Award and University of the Year for student employability, and so on and so forth. The research impact really stayed back from the early 80s. The University of Surrey continues to contribute to society through the breakthroughs and innovation. For example, University of Surrey is home of the first small satellite in the world. That was in early 80s. I'm not sure you can see the cursor. Okay. Use a laser pointer. So you can see the from that time, and also the quantum well laser, also invented by Arthur Adams there in the mid 80s, early 90s. It's been used for internet streaming. This is behind the optical fiber streaming, to the latest machine learning algorithm to turn sign languages into English. As well as the 5G, first 5G controlled autonomous vehicle on our campus was realized in 2017. So recently we set up the Surrey Institute for Sustainability, that is bringing a multidisciplinary approach to tackle the grand challenges in society, to look at the systems approach to society's nature feedback loops, or energy, water, and food nexus, the societal changes or culture changes for sustainability in terms of sustainable living, and also infrastructure. We bring together from all 3 faculties capabilities in clean air, clean energy, transport, water, and sustainable food and energy systems analysis and public health. So today's talk is mainly relating to a very, very hot topic, that's the energy and climate. Because if you look at the late Rick Smalley gave a talk many years ago in Congress, in the US Congress, really setting out the top 10 challenges for humanity in this century, really in terms of these 10 problems. Of course, population is underpinning a lot of these problems, or contributing to a lot of these problems. Energy is at the top problems, and energy, the whole energy sector, and of course that linked to climate change, is the biggest challenge that we face. So you may be familiar with the concept of the decarbonization or transition from the fossil fuel to hydrogen economy. It really is a trend that we've been really witnessing, and we've been doing a lot of innovation, research innovation for a long time. That is to do with the decreasing the carbon in our fuel systems to from the wood, coal, oil, and the hydrogen to carbon ratio is increasing. Eventually, it will be pure hydrogen. But where does hydrogen come from? The hydrogen eventually will rely on renewable resources, renewable energy to convert water from electrolysis or direct conversion of photon energy to hydrogen through photocatalysis. And then you can utilize the hydrogen using fuel cell or using hydrogen in other form to drive vehicles, aviation, as well as shipping. Okay, hydrogen, we're all familiar, was discovered twice, in fact, in the 17th century and also in the 18th century. The latest, of course, Cavendish, who actually not only discovered the property of hydrogen, but also quantified many of the atomic structure and also the other properties. Hydrogen is produced today from natural gas, oil, coal, and electrolysis, but predominantly from natural gas. About half of the hydrogen produced is from the cracking of natural gas using a thermochemical process. So it's still a very low quantity, about 70 to 80 million tons per year is produced. So when you use fossil fuels, when you use hydrogen or coal, for that matter, to produce hydrogen, it's called the gray hydrogen because you generate carbon dioxide. But if you sequester or capture the carbon dioxide, and that's labeled as a blue hydrogen. Of course, we know hydrogen doesn't have a color, but and then if you make hydrogen from electrolysis, and that is decomposed water, that's the so-called green hydrogen. In terms of demand, the International Energy Agency has predicted by 2070, and let's say from 2050 to 2070, we will need a lot of hydrogen in terms of millions of tons of oil equivalent per year. So it's about 1 billion tons of oil equivalent. And these are the different sectors, right? So the transport sector in terms of ammonia, electricity, hydrogen, buildings, and so on. So the main the sectors that will use hydrogen the most will be shipping, aviation, and road transport. The other sectors, of course, chemicals will use hydrogen as well. The US DOE has produced a roadmap some years ago, back about 10 years ago. In terms of the phase 1, phase 2, and phase 4, phase 1 is already passed. So technology development, research to meet customer requirements, establish the business case, leads to a commercial decision. And then the initial market penetration started, now start to penetrate because many countries start to produce hydrogen from renewable energy sources. Infrastructure investment, which is a key, and I'll come back to that. And also the market and the whole deployment of hydrogen, which is happening from now, approximately now, until mid-2040s. So by the 2050s, we will have a full hydrogen economy in terms of the production and distribution and the utilization. So this chart, this slide shows you the hydrogen sector value chain. So from hydrogen production, storage, to the equipment, infrastructure, supply chain, to application then. So distribution is also quite important in terms of how you're going to distribute to the pipelines or to store compressed tanks, as well as the hydrogen refilling stations. The different ways of storing hydrogen, I will return to this topic on the hydrogen storage options later. And of course, the green, blue, and waste, and the geosequestration, carbon capture is also part of the whole energy or hydrogen sector of supply chain. The technical economics of hydrogen production is very clear. At the moment, green hydrogen, that is to convert solar, wind, and other renewable to hydrogen, is about $3 to $6 per kilogram of hydrogen. Where gray hydrogen is you convert methane into hydrogen is about $1 to $2. $1 to $2 is commercial value. Now it's produced for chemical industries and for other uses already. So this is the natural gas steam reforming route. But if you use biomass, it's even higher cost. So biomass conversion to hydrogen is prohibitively expensive. But in the future, so we're moving towards the technology innovation, including materials innovation, which is key, to reduce the cost of green hydrogen to about $2 per kilogram, then it'll become competitive. So this is a cartoon to show the green hydrogen production. So renewable energy, electrolysis, and then move to hydrogen storage, fuel cell, then drive the vehicle. And this cartoon in the PNAS article a few years ago, it says the liquid sun, or liquid energy from the sun, but it can be liquid, it can be gas. Of course, when we have hydrogen stored in ammonia, it is liquid. But the cost, why is so high? Because the electrolyzer will lose energy efficiency. Today, 80% of the efficiency loss, or the 80% of the cost reduction can be realized, is actually exists in the electrolyzer. That therefore is a challenge to further develop new electrolyte and the electrode technology in electrolyzers, and like fuel cell development is already quite successful. But the electrolyzers, there are many different types of electrolyzers. The conventional one is liquid, it's alkaline, which is very established, but has a fairly modest efficiency. It's about up to 70%. 30% of the energy, is actually lost. Whatever energy, put it solar energy or wind energy. But there's a promising proton exchange membrane. It's the solid state membrane technology. For those who are familiar with this technology, is very promising. It's an early stage commercial demonstration, can go up to 82%. And of course, in the longer term, is the high temperature solid state. This is the reverse solid state fuel cell. So basically, it's the oxygen ion as the charge carrier. And you can actually, now is in demonstration, can go up to 100% efficiency. And of course, there are a lot of technological challenges, many of which are materials. For example, the solid oxide needs to operate at high temperature. Any ceramic, solid oxide, you are familiar with this, will crack. Mechanical stability is a big problem. So this is an engineering challenge as much as a materials challenge. And therefore, we need to look towards, alternatives. While we improving the efficiency, reducing the cost in electrolyzers, we need to improve other technologies such as direct photo catalysis to move towards direct conversion from the solar energy to hydrogen, therefore to minimize the losses. So this is the top one is the centralized, of course, natural gas reform, which is the conventional, and biomass is here, moving towards a solar to hydrogen conversion, and then photo electrochemical process, and distributed, similar kind of route, but the solar pathway is the future. In terms of the future, I think you'll be familiar with the photosynthesis. The artificial photosynthesis is really this process here is a photocatalysis. So that is something I'm going to talk about The solar vision is really to use solar, which is abundant of energy that irradiated on the Earth's surface. And of course, we have solar voltaic technology has come a long way, become very, very cheap. But you could also imagine, imagine that you can directly convert solar, the photon energy, into chemical energy. The chemical energy is hydrogen or methanol or ammonia. And this has an advantage in terms of distribution. It has an advantage in terms of utilization. That is not just electricity, but then you have to store electricity in batteries. The possible route for solar hydrogen production are multiple. Of course, the heat from the solar energy can be utilized, and that's from the mechanical energy utilization or thermolysis processes to produce hydrogen. Or you use the electrolysis, which I mentioned, or biomass conversion to hydrogen and photocatalysis, and directly splitting water into hydrogen and oxygen. Solar to hydrogen, there are many systems already. This chart shows the efficiency was the technical complexity. And this is a technical complexity is high to low and efficiency from low to high. The ideal quadrant is this here. That's the practical solar hydrogen production. We need a minimum of 10% solar to hydrogen efficiency. 10% is the challenge. At the moment, photocatalysis is only 1%. So we need an order of magnitude increase in efficiency. And the PV and the electrolysis already have a high efficiency, but it's high cost because of the technical complexity. Yes, it's all here. So anything in between is the photoelectric electrical conversion process, which I also have an example to show. Now, the long-term holy grail for hydrogen production from solar, as I mentioned, is photocatalysis. Photocatalysis, for those familiar with catalysis, is a surface phenomena, and the chemical reaction is happening on the surface of a nanoparticle, in this case, a semiconductor nanoparticle, like titanium nanoparticle, or any other semiconductors. When you have photons irradiating on the surface, the electrons and the hole will separate. The electron hole will recombine in the bulk and also on the surface. And the trick is to really enhance the light harvesting, which is actually to do with the electronic structure of the semiconductor, and the charge separation and transfer process efficiency, and the surface reaction. Bear in mind, they operate at a different time scales. So I'll come back to that. The solar to hydrogen efficiency depends on these three factors. And we have done a lot of work in my own research lab in Australia. We look at how to engineer photocatalysts to give you the best properties and best performance for different applications. For example, for applications to convert the photon to electricity, which is a dye-sensitized solar cell, which you probably familiar. And when you actually want to use the hole as a highly oxidizing species to oxidize pollutants in water and air, and you have this photocatalytic reaction, oxidation reaction. And then you can also actually directly use the reduction power to produce hydrogen by splitting water. So a lot of these key properties we can optimize, and now I'll come back to that. So in terms of the engineering of a nanocrystalline photocatalyst, we can actually use heterostructure techniques and doping techniques and crystal growth techniques. So they respectively control ultimately the interface carrier transfer through heterostructure and through all these mechanisms. And the doping will eventually modify the surface redox sites. And then the crystal growth will eventually improve the surface state conducive for the different applications. And we have done many projects in those three domains, trying to optimize the structure, the electronic structure, the crystal structure, and the surface structure of a photocatalyst. One of the publications, one of the early work we did is to engineer nanocrystal of titanium, which is anatase crystal, to have a highly reactive surface in a preferential way. You grow those surfaces in a stable way. So these are the crystals that we developed, because according to Michael Brizzle from ETH in Switzerland, so the crystals has a low index surface, like 001 phase or 010 phase, is highly energetic. It can actually split water much faster, and but it's very difficult to achieve. They did the calculation publishing physical review letters in 1998. We were the first to realize this in the lab by growing these crystals, and we can actually tailor the crystals to have lower index and more of this flat surface, which is the 001 phase. And then this elongated phase, which is here, that's the top. You can also produce this kind of elongated crystals that has a 010 phase. And we found for hydrogen production, in particular, the hydrogen production from water splitting, the 010 phase is more favorable, has the highest photoreactivity than 101 phase, than 001 phase. And because of the favorable electronic structure, and therefore enhancing the transfer of the strong reducing electrons on the conduction band, then therefore will produce and accelerate the hydrogen production. So I mentioned about the time scale. If you those in the audience familiar with solid state physics, the time scale in a semiconductor photocatalyst in photocatalysis process, this is really complex, from femtosecond to second. So when the photon hit the surface, and that is happening in a femtosecond, and then the charge separation transfer is a nanosecond to microsecond, and of course the surface reaction is happening within seconds to minutes. So that is something that's very important in terms of balancing, or maximizing the efficiency of solar to hydrogen efficiency in terms of absorption, the separation, transfer, and reactions. Right? Ultimately, you want to improve this efficiency from 1% to 10% to find the optimal structure that you can increase this. Oh, sorry. Okay, so we have done some work in this area trying to heterostructure the interface of two different types of semiconductor. For example, zinc oxide and zinc sulfide. So this is this all solid state Z scheme. So you can actually inject into the conduction band, and eventually you have the better interface between two semiconductors, so that you can have a good match in terms of the energy band, so that you can maximize. So we've done a lot of work from 2009 to even now. My postdocs still continue in their own groups now for this kind of work. I just want to show you one system that is using a cold shell nanoparticle that is zinc oxide and zinc sulfide coated on a metal cadmium core. So it's a cold shell particle system. And let me see whether this will go. No, it doesn't go. I think I have to. Pointer. There's a video here, but nonetheless, This is the best photocatalyst for water splitting to produce hydrogen at that time, around 2012, 10 years ago. Of course, the efficiency is still 1.5%. So improved, but not enough. So that is the work. And then we also did a lot of work on electrochemical water splitting, because this is an energetically uphill reaction. So you need to have some electrical energy input, because the bias, you can actually generate the hydrogen and the oxygen separate, using a membrane directly in this kind of reactor. You could also make a artificial leaf with a tandem solar cell, the photovoltaic cell based on perovskite. In this case, it's a perovskite solar cell with the artificial leaf, which is a solid state co-catalyst system using this kind of system here as a dual electrode to produce hydrogen. And then we achieve the hydrogen efficiency 6.5%. So getting closer to the 10% efficiency. Right, now moving rapidly to the hydrogen storage, as I talked about the whole supply chain and then the value chain. Hydrogen storage is very important. It's going to be the bottleneck. You can produce the hydrogen, but hydrogen storage can hold you back. And because hydrogen storage will determine how you store hydrogen, will determine how you refill. Because at the moment, electrical cars has become more and more popular, but charging is actually quite tedious, takes time. But hydrogen fuel cell cars, if you can use a cartridge swap, will be just within 1 minute, and that's the desirable. Or if you're going to charge using compressed tank, and this is the relative to a car, the size, this is a 200 bar here, this drum, imagine you have that big drum in the car, and the thickness of the tank will have to be very thick for safety reasons. But if you use liquefied hydrogen, you will lose 1/3 of the energy during the production of the liquefied hydrogen, handling, evaporation, and then the cryogenic energy you required. And then, therefore, solid state, which is, let's say metahydrate here, give you 5 to 10% weight energy, and that is very promising. But then you have a different problem. You have to drive the hydrogen off to fill the fuel cell. So this is kind of the Ragon plot. Basically, is the energy density and the hydride systems here. So basically, this is the challenge of hydrogen storage, right? At the moment, all the buses, the cars using fuel cells, they use a tank, right? But you have the weight problem and you have the volumetric density problem. So hydrogen storage, the US DOE also set a target. The US DOE target in terms of 2025, which is another 2-3 years, is in terms of the mass is about 5.5%. In terms of the system, volumetric capacity, this is the number, and in terms of the whole system cost. So this is the target. I think there are a lot of companies trying to develop the alternative technology in terms of the solid state materials, not compressed gas, which is mature. Liquefied hydrogen, as I said, is a lot energy wasted. So the IEA benchmark is 5%, and both 5% and 50% in terms of volumetric density. But practically, you need to drive the hydrogen off. So the requirement is no higher than 150 degrees. Why 150 degrees? Because the fuel cell waste heat can give you about 100 to 150 degrees. You can use very, very conveniently to drive off the hydrogen from the solid materials to feed into the fuel cell. But you also in terms of the charging and discharging, you also need the time to be less than 5 minutes, as we now doing our refilling for our petrol engine car. So there are many, we did a lot of work in this area. One of the area we explored is metal hydrate, but with a catalyst, with the carbon nanotubes or other metals, biometallic catalyst to enhance the storage. So we have developed systems that actually with the catalyst around here, it gives you almost 5% capacity, and the desorption temperature within 60 minutes. This is within 50 minutes is 5.2%, 200 degrees C, but 150 will take longer. So that therefore this is still not ideal, but it's getting very close to the DOE target. Finally, this is about the future. I think the future, there are many materials innovations happening around the world for storing hydrogen to achieve the DOE target, so that you can store hydrogen at 2 bar instead of 200 bar. And you can store that and then store the hydrogen at room temperature and drive off the hydrogen at about lower than 150 degrees C. The most promising system is molecular absorption mechanisms in terms of the metal organic framework, biometallic complexes, the most promising systems in terms of driving this diagram plot. Metal hydride systems are already there in terms of capacity, but the temperature needed to drive hydrogen is very high. And therefore, there's a lot more research and innovation to be done. Finally, I would like to say that as engineers and scientists, we do fundamental research developing novel materials, but in order to really make the materials useful and to be commercialized, and I learned a lot today by visiting Jerusalem and talking to Gabo as Institute of Nanotechnology, Nanotechnology Systems. You need to really take from the application side the requirement, and then look at how you then engineer the materials and then optimize the materials that become useful. That will take to the market much faster. Similarly, I think from the Dixon's article, this is almost 10 years, about materials to market, is still applicable to hydrogen materials. That is to look at this loop. Of course, you start with the market needs, societal trend, the market needs, and then you actually do this innovation loop. So informed by the market, and then what kind of system performance requirement, once you put into a system, not just the materials, but it's in a device, in a car, for example. And then, of course, you look at how, at the molecular atomic level, how you optimize the properties, and then drive the performance, improve the performance in the system level, and then to the market. This is a iterative process. Sometimes takes many loops. But importantly is to work in collaboration with those people who are doing business and who are doing marketing. So otherwise, even if you develop a wonderful materials that has best performance, it cannot be marketed because of the cost or other factors, the market issues. So I guess the lessons we have learned is that, okay, we develop a lot of materials, but we also patented many patents. And then the few startup companies out of my lab in Queensland, in Australia, did not survive the first 5 years, right? Because there's a lot of things behind the marketing, behind the business development, and so on and so forth. So with that, I'd like to thank you very much for your attention, and I'd like to say once again, it's a great honor to be here and to be part of the family of the Academy. And it's such a great honor. Thank you very much.
No doubt that we're going to have many questions to do, but I would like to invite everybody to go to our library. I have some personal questions and go with him and hear all your questions or comments that you want to. Okay, thank you very much, Mr. Duke, and I invite you to go there. Muy bueno.
Muy bueno.
Sí, ya me parecía que estaba regularizado.
Soy más viejo.
No, no, pero me pareció, no, porque miré y digo, sí, los rasgos son. Gracias a Dios por no la veíamos. Sí, puede ser.
Vos seguís viviendo.
Sigo viviendo.